Now, when we look at a crystal, and crystal is what? A regular arrangement of the particles. Fine. That's what sets a crystal apart from an amorphous solid. We have seen that. Well, that's a different thing. Why? If you have seen a crystal glass and if you see a normal glass, you'll find a hell lot of difference in the clarity of the two glasses. You can just by seeing, you can tell that this is a crystal glass and that's a normal amorphous glass that we see, and it is that cost that you're paying for making an unarranged, disordered system into an ordered system. That's what you are, and more ordered it becomes, the more clear it becomes. So much so that there is a proverb in English saying crystal clear. Okay, as clear as the crystal. The concepts are crystal clear. It means absolutely clear. Fine. The reason is that. So a crystalline solid is what we have seen earlier. It is a regular arrangement. It's a regular arrangement of particles. Regular arrangement of particles. Okay. Now, for understanding sake, or even otherwise, when compared to the dimensions, we look at the crystal. What happens? We represent the particles as points. Okay, we represent the particles as points. We represent the particles as points. Okay. Okay, we represent the particles as points. Okay, as points, and we join those points to understand what the shape will be. Those joinings, you can say, are maybe the chemical bonds that are holding them together. Okay, but otherwise we just join them. So we represent the particles as points, and when we make a 3D structure of that is what is called a lattice. Okay, a three-dimensional structure. So crystal lattice is nothing but a three-dimensional structure of points which represent the particles, and the particles can be what? The particles can be atoms, molecules, or one of the most famous, the ions. They can be anything. Fine. Now, the lattices, they are of but one more thing. If you can segregate out one unit which when replicated in the 3D gives you the whole lattice, that is called the unit cell. So a representative smallest unit of the lattice, that which when replicated everywhere in the 3D, replicated everywhere in the 3D, gives the lattice is called the unit cell. It is called the unit cell. Okay. It's called a unit cell. That is the smallest part of the lattice. Fine. So I am okay. Now about the lattices, there are 14 3D lattices possible, and they are called Bravai lattice. Bravai lattice. After the fellow who explored them. Now, for completeness sake, let me write the characteristics of lattice. Each point in a lattice is called a lattice point or lattice site. Okay, these lattice points could be molecule lattice points, could be atoms, molecules, or ions, and we join the lattice points by straight line. Lattice points joined by straight lines. By straight lines to bring out the geometry. Okay, to bring out the geometry of the lattice. Okay. When we are dealing with the unit cell, we have our own conventions, and the convention goes like that. This. Okay. And okay. All 3D structures with straight lines are made simply by drawing 3 lines and then keep on drawing lines parallel to them. So in this case, a vertical, a horizontal, and one at somewhere around 45 degrees. Fine. If it's a rectangular thing that you are looking at, then wherever you go, you just keep on drawing lines parallel to them. Only these 3 lines. Fine. If they are all straight edges cutting at 90 degrees, then this is the way to do. So I draw this line which is parallel to this, I draw this line which is parallel to this, I draw this line which is parallel to this, parallel to this, parallel to this, wherever you extend, it will be that. Then it will become very easy to draw the diagrams. This is in engineering drawing terms called orthogonal projection. Okay. So it is something like this. Also, this is a rule in engineering drawing to draw the edges that are not seen as dotted. We draw them as dotted. Okay. Now, you should also understand one thing. These three are nothing but the x, y and z coordinates of a right-handed system. What do you mean by a right-handed system? Where I cross j gives you k cap. Okay. There are two ways in which you could have named it. If I flip this x and y, then you know I'll be wrong. It'll become a left-handed system. So if the positive direction of the x-axis goes on to the positive direction of the y-axis through the smaller angle, and that is the direction in which you move a right-handed screw, then the right-handed screw should move in the positive direction of z-axis. Does it do that here? Our x-axis is out like this, our y-axis is this. Okay. I bring my x-axis onto the y-axis through the smaller angle. There was this angle also, the bigger one, 270, reflects 90. Here, looking from up, an anti-clockwise movement. Okay. If I open a normal bottle with a lid in anti-clockwise, what happens? Linearly it comes towards us or down? Towards us. So that is the direction of the z-axis. Fine. So we are dealing with a right-handed system. Now what we have done, we have named these as the x-axis as A, the y-axis as B, and z-axis as C. Okay. So the line segment of that cube that falls along the x, y, z have been named A, B, C. Fine. Now let there be no confusion. If I had put this as x and this as y and this as z, then too I would have got the same thing. But in any standard text, they take the horizontal, the lower one, that means the plane on which I am standing, the floor, as the xy plane. This is a mere convention. Okay. It's not to say that you could not have taken this as x-axis and this as y-axis and this as z-axis, so that this would have become A, this would have become B, and this would have become C. That's not to say that. Okay. So but we take the black ones, not the red ones. Okay. And how have we defined our alpha, beta, gamma? The A comes in. Okay. So you move along A, hit the point of intersection, whatever is the opposite angle, that is alpha. Okay. That is alpha. Come along B, whatever is the opposite angle, that is beta. And come along C, whatever is the opposite angle, that is gamma. We have to be methodical in the first time we are defining them, because otherwise what will happen? It will simply become very, very, very chaotic. So this is something that we freeze at this point and we understand why. Okay. So what I am saying is that a crystal a unit cell is characterized by the following. A unit cell is characterized by the following. What is the first thing? Edge lengths are designated. Edge lengths are designated A, B, C. obviously along x, y, z axis.
So why is it given that it may also not be, it may not be mutually perpendicular?
It may not be, because it could be a parallelopipe kind of thing. That could also be there, no? For example, it could be something like this, no? It could be a, you understand, this cross section that is there, here it is a square. If you look from above, if it's a rhombus, then what happens? They're not mutually perpendicular. Okay. Because we have to take into account everything that we come across. So that's why they have said not necessarily mutually perpendicular. And angles alpha between B and C, beta between C and A, gamma between A and B. Okay? That's how we define it. Fine.